Hello everyone. Yeah, thanks for the invited talk. So I'm Hengshuang from Hong Kong University. So today I'm going to talk about our recent works on vision foundation models with spatial intelligence. So during the past years, we have witnessed the development of large language models. For example, back to 5 or 6 years ago, we had GPT-3, and after that, we have lots of powerful large language models. For example, we have ChatGPT, GPT-4, and so on and so forth. So apart from this closed-sourced toolkit, we also have some open-sourced large language models. For example, we have Llama, Llama 2, Llama 3, and so on and so forth. So recently in this year, at the beginning of this year, we have DeepSeek. So large language models, we have witnessed the powerful ability and generalization ability, reasoning ability of these large language models. And based on these large language models, actually we can combine other modalities into these large language models. So we can have multimodal large language models. And one of the important modalities is vision. So we have computer vision. So sometimes we can also say that we have large vision language models. So for example, some of the works including Flamingo. So back to about 3 years ago. And after that, we also have some outstanding or milestone works from our academia, from universities, for example, Lava and Mini GPT-4. And we also have some, for example, Gemini and so on and so forth, and GPT-4 and so on and so forth. Actually, in this field, it's still developing rapidly. So for example, for these foundation models, we either for 1D, 2D, or multimodal, some of the representative works, including, like, for example, Google Stat and Llama and the GPT-N series. And for vision models, we have some, for example, the Florence. And back 2 years ago, we have the most popular model, segment anything model. And for representation learning, we have Dialog, Dialog-V2, Signip, Signip2, and so on and so forth. And for multimodal models, we have Clip, we have DALL-E, and we have Flamingo. So the success of these foundation models mainly comes from the structures and at the same time from the data. So for example, when we're trying to train 1D foundation models for language models, actually, for example, we can have lots of high quality text data from the website, from Wikipedia, and also from the literatures from all around the world. And actually, as we may be aware, so nowadays, actually, every day we are producing lots of papers. For example, last year's news, we have published more than 4,000 papers. And in this year, CVPR, we are accepted nearly about 3,000 papers. We are producing high quality text data every day. And similarly, in vision, we have some high quality data. For example, we have ImageNet. And for per pixel labeling, for pixel level understanding, so this is pixel level foundation models. So for pixel level understanding, we have, for example, we have COCO, we have 8020K, we have cityscapes, and so on and so forth. And apart from this annotated data, we also have vast amount of images that are not unannotated, so which can also be utilized to train the models. For example, when we train Dialog, and we also have lots of weakly annotated data. For example, we can train Clip and so on and so forth. So these powerful models, these foundation models are very powerful. So the question is, are all the problems solved for our vision community? So actually, we tested some scenarios. For example, so in a given image, we test the latest AI agent. So which option best describes the thing contained in the image? The agent has given 4 descriptions, and you are asked to select the correct answer. So the agent selects the one answer, C. So the first statement, that one giraffe is walking towards the left side of the camera. So that's correct. But for the remaining one, while the other one is walking away from the camera. So this is not correct. Actually, it's walking towards or facing and walking to the camera. So the current models have issues when trying to understand the direction. So we have more cases. For example, which option below best describes the relative position of the black bears? So actually, the agent selects the answer B, so which thinks the middle one is higher than the other ones. But actually, the correct answer is that the two birds actually they are standing on the foreground. They are on the same height of the wooden structure. This is according to our common practice in real life. So actually, they have some issues when trying to understand the relative depth. So for the next one, actually, we want to identify is that. So for some indoor scenes, for example, in the dining room, so we are trying to identify the relationship or the relative relationship of the two glasses filled with the white vin. Yeah, so actually the agent thinks that they are of the same height, but actually the glass on the right one is taller than on the left. So we have issues when trying to understand the relative size and so on and so forth. For example, how about this situation? So for complex testing understanding, so the wrong answer the agent selects is that the cat is lying on the sofa with two front legs reaching out, but actually only one front leg is reaching out. So have some problems when trying to understand the complex scenarios for indoor and also for outdoor scenarios. For example, so this is quite common things in a parking lot. So it is important for self-driving. So only 3 stop signs in a straight line. So the agent thinks that they are not in a straight line, they are in a zigzag pattern. But actually, to our humans, actually they are in a straight line. So the agent have problems when trying to understand the spatial relationships. So today's talk, we are focusing on trying to explore foundation models with spatial intelligence. So actually for this topic is relatively underexplored, but for our humans, actually we are living in a 3D or 4D world. Actually, so the spatial intelligence will much augment our humanity. So we are trying to figure out this issue in 2 different domains. So previously we have witnessed powerful models in 1D and 2D and multimodal, but less of them are working on high dimensions or on spatial intelligence. So we are trying to figure out 3D and 2.5D models. But there are some challenges. For example, the data format. So compared to 1D or 2D data, the data format in 3D and 2.5D is much more difficult to handle. And also at the same time, the data size is quite limited compared to we have vast amount of 1D and 2D data, but for 3D and 2.5D, it's quite limited. So how to develop raw operators, backbone structures, and powerful representation learning algorithms remains lots of challenges. So we want to figure out these issues. So the first part we want to figure out is spatial understanding, trying to understand the surrounding things. So actually nowadays, our world is 3-dimensional and we are surrounded by 3D things. So processing and learning the 3D data has lots of potential important applications. For example, it can be utilized in autonomous driving, robotics, augmented reality, medical image analysis, and so on and so on. Yeah. So for 3D data, actually different from 2D images, which are placed pixels in regular grids, while 3D data, they have different representation types. For example, we have point clouds, we have mesh, we have volumetric, we have projective view. So among all these different representation types, different data representations, the point clouds is a raw sensor data, and it can be easily transferred to other formats and vice versa. So our target is trying to figure out a solution for point clouds. Yeah, so point cloud can be easily captured by lots of hardware in different scenarios. For example, we can use LiDAR sensor in self-driving things. We can use laser scanner in indoor things. We can also using videos, IGBT videos. For example, we can using VGGT to extract the camera pose and also point cloud from videos. And we can also using SNAP system. And actually, so nowadays we have lots of wonderful simulation platforms. So that contains lots of existing 3D models. Yeah, so actually we can also extract point cloud for model access. So point clouds can be acquired from a diverse range of sensors from existing assets. So we have point cloud, but in contrast, the 3D point cloud actually they are unworded and scattered in 3D space. So they are essentially sets, and the conventional canvas is not available now. They are not applicable anymore. So learning-based, so we are trying to figure out a solution. A learning-based approach can be roughly divided into the following types. So for example, when we are trying to processing the 3D data, actually one direction way is that we can just do projection. So we have projection-based method. For example, given a point clouds, we can have different image planes and we do projection. So in this case, we can transfer the 3D point cloud into multi-view 2D images. And after that, we can use some existing 2D neural networks, for example, 2D coverlet or 2D VIT to extract the features. And after that, we can do multi-view feature pooling or ensemble and finally get the results. But there are some problems, for example, so how many cameras to choose and how to decide the image planes when we're trying to do projection. So this is the problem. But also at the same time, so as we may be aware, there are lots of branches from the 2D to the final representation. So the computation cost will be a problem. And for the third time, so actually, so the most important property for 3D data is the geometry property. But after projection, this important property is lost during the projection. Even we have some view pooling solutions, but this cannot recover the full geometry property. So this is an issue. So apart from doing projection, another way is that we can do voxelization. So we have some voxel-based methods. So actually we can do 3D voxelization, then followed by convolution in 3D. So some of the representative works, including voxellet or octalet, sparse conlet, and minq-ulet. So we can use these kind of methods to process the 3D data. Yeah, but there are some problems. For example, when we are trying to apply this method naively, actually this strategy we can meet some problems for massive computations, since the computations will increase in a cubic growth in the number of voxels. Yeah, and also at the same time, this solution is that when we do voxelization, there are some quantization errors due to the methods. So another way is that we can directly working on the point cloud. So we can use some, for example, order invariant or permutation invariant operators. For example, we can using MLP and pooling layers. So some of the works, for example, the milestone works are pointer-nets, pointer-to, DCCN, and so on and so forth. But the problem is that this kind of raw operator is not powerful enough. Yeah, MLP is not so powerful enough. So we are trying to figure out a better solution and more powerful solution to model 3D point clouds. Yeah, so actually we start from some property analysis. For example, actually we find that the self-attention is a good fit for these kind of problems. For example, so no regular grids needed as in convolution. Yeah, for convolution, when we're trying to deal with 1D and 2D data, so regular grids is needed. And then position encoding is quite important for transformer or self-attention structures. And for our 3D point cloud, actually we have 3D coordinates that can provide strong position information. So this is a good fit. So actually we have some explorations. So first one is back to 4 years ago, we developed the first version of point transformer. So it can be utilized as a backbone structure and can be utilized to multiple tasks. For example, we can utilize it for shape classification, object segmentation, path segmentation, and semantic parsing. Yeah, and after that, so the main contribution is that we have a kind of vector attention operator and also the point transform layer. So the next thing that we want to further speed up the processing steps. So remember that our target, we are trying to develop foundation models with spatial intelligence. So the efficiency is important. And at the same time, so our model can hold vast amount of data. Okay. So next step, so back to about 3 years ago, we have the second version of point transformer. So we make some modifications. For example, we have the group vector attention and also partition-based pooling. And then, so last year, we have our third version of point transformer. So CVPR 2024. Actually, so this one actually is more powerful than the previous, the first and second version. So what we have done, okay. So actually, we're trying to figure out the latency of the existing solutions of the previous methods. For example, we draw the latency tree map of the PTV2, and we find that there are some inefficient designs. For example, the KN query. So when we are trying to deal with the unordered sets in 3D space, so one important thing is how to construct the local relationships, the local neighboring hood. Okay, so actually previously we are using FPS, fastest point sampling, and then followed by KN. Yeah, KN is the labels. But well, we find that about 28% of the latency comes from this part. So result difficulty in parallelization. So actually we want to do parallel computing. We want to speed up the processing and the computations. So actually no accurate labels are needed by our method or by the kernels. So what we need is to do relatively precise, and we are trying to enlarge a receptive field, as we may be aware. So understanding, yeah, so the understanding task receptive field is quite important. Yeah, for example, in 2D detection and segmentation and so on and so forth. So this is also important in 3D and 2.5D. So inspired by some recent works like octoformer and fatformer, so we break the curves by serializing the point clouds. So what we did, so we are trying to transform the unstructured spatial representations in 3D to structured data representations in 1D. So we use some classical solutions in computer graphics, for example. We can using a space filling curve, okay? So in this case, actually, all of the data points are connected in 3D space, and then these unordered sets can be transferred to ordered sets. So we have the ordered point clouds and the structured 1D data. And after that, actually, we can do patch partition. Yeah, so which can maintain the spatial relationships between the neighboring point clouds. So the major difference is that we have the point cloud realization. For example, so previously for point transform V2, okay, we are using the k-nearest labels. Okay, so or sometimes we are using the ball query, but for this case, the receptive field is quite limited. So usually we have about 16 and or 32 number of labels. But compared to that, when we are using space filling curve, we can much increase the receptive field. For example, we can increase up to more than 1,000 or 4,000. So this is quite important, especially if we want to dealing with, for example, if the input point cloud contains more than 1 million number of point clouds. Okay. So actually, we have different choices for the order. For example, we can have the z-order curve, we can have the Hilbert curve, and we can also have the transpose curve of these two versions. And we can combine all of them together. Yeah, so once we have these orders, we can do reordering. For example, in the unordered sets, we can use these curves. We do reordering. Now we have the ordered 1D data for parallel computing. Okay, and sometimes we can also do padding. So this is similar in 2D. And yeah, so some of the tricks and also some of the good designs from 2D can also be applied to 3D, to this kind of 1D data. For example, we can have the dilations. So dynamic count from 2D. And we can also do shifting, and also we can do shuffling, and we can also have some design similar to swing transformer. We can have the sliding windows and so on and so forth. So we can actually, for different patches, we can have patch interactions. Okay. So for our final result, actually, we can enlarge the receptive field. So we have a wider receptive field compared to previous versions. And at the same time, since we are trying to figure out a solution for 3D foundation model, so the efficiency is also important. So we want to have the faster speed. So compared to the previous version, so actually MIC-UNet is much faster than PTV2, but now we find that PTV3 is much faster than PTV2, and even faster than MIC-UNet or sparse converlet. Okay, nowadays, so GPU hours is quite expensive. So we also want to, if we want to scale up, so GPU is also important. So we can much reduce the memory consumption. For example, so we can save about 10 times GPU memory. So we do testing on multiple data sets and also multiple benchmarks. For example, for indoor and outdoor scenarios, for different tasks, for segmentation, detection, instance, and so on, for indoor like SVDS and ScanNet, for outdoor things in autonomous driving especially, we have KT, semantic KT, new things, Waymo, and so on and so forth. Actually, we can get a better results compared to previous solutions. So as you may be aware, so previous solutions actually for indoor things, so some of the methods can only apply to indoor things. Some of the methods can only apply to outdoor things. But our method is a unified solution to things in different scenarios. So actually, we also participate in the Waymo challenge in last year's CVPR, and we are the winner for this challenge. But what we are doing beyond the 3D point cloud understanding, actually, we are doing unstructured element modeling in high dimensional space. So beyond this scope, actually, we can also apply into more fields, into other fields, for example, AI in AI for science. So we can also might be utilized for weather forecasting, catalyst discovery, and object discovery. So in this field, previously the best solution is we are using graph neural network. But for 3D point cloud, we have already witnessed that the point transformer is much better than existing graph neural networks-based solutions. So this might also be benefit in this field. Yeah. Yeah, so we have just introduced the 3D foundation models. So yeah, back 2 years ago, we have the powerful 2D foundation model, which is also a pixel level foundation model, segment anything. Yeah, so we have witnessed especially the generalization ability into, for example, the crowded scenarios for indoor things and outdoor things. Yeah, so beyond between 3D and 2D, the next thing we want to figure out is 2.5D, which is the depth information. So the depth can actually, we can have different ways to capture the depth information. For example, from the RGB images, from the LiDAR sensors, and we can also use some existing depth models, for example, meters. So what we found, that for segment anything, it shows great generalization ability for high-level vision tasks, which is segmentation. So it uses vast amount of data. So data scaling or first we visit this as success in 1D. Now we also visit this its success in 2D high-level vision task. So we want to bring this idea or data scaling or in 2.5D. So what we found, okay. So currently the labeled images for depth estimation is quite limited, only contains about 1.5 million number of images and the corresponding pairs. But the successful depth for segment anything is that they have up to billions number of images and segmentation mask. So we want to use vast amount of unlabeled images. So as shown here, we have about 62, we use more than 62 million number of images for depth estimation. So what we did, actually, we are using a semi-supervised learning algorithms. So we have some labeled images from existing data sets. Okay, we have vast amount of unlabeled images or web scale unlabeled images from website from online. Okay, so we can have the shared encoder, and then we can have some unlabeled images or unlabeled procedural labels. Then we can train a teacher model to teach a student model. And finally, actually, we can get a good performance. For example, these are some of the illustrations here. So we have our depth anything model. So we test it on different scenarios. For example, this is on the indoor scenarios. So for example, in the middle, so so they are crowded scenarios, but we can get accurate depth estimation. And for the final one on the right, actually this is in a low light room, but actually we can still identify the computer desk from the original image, but it is even challenged by our human beings. Okay, so apart from indoor scenarios, we're also testing on outdoor things. For example, for these buildings and highways, actually we can also get accurate depth estimation, and it has lots of applications. So we also do some testing we are trying to boost the generalization ability. So we'll also do some testing, for example, on oil painting or AIGC generated images for abstract images, for example, so compared to previous best solution, which is Midas, which is also very powerful. But when testing on this kind of AIGC or oil paintings, actually their performance is not so good. Well, for ours, we can get the accurate depth information or geometry property of the input images. Yeah, for more complex scenarios in real things, for example, for the mushrooms and plants, actually compared to Midas, our result is more accurate, yeah, more detailed structures. And we also do some testing in video scenarios. So for the frames, it predicts frame by frame, okay? So if you pay attention to the background styles, the wooden structures, actually our method can still identify these detailed structures. So this is compared to in the middle, actually all of the background are mixed. Yeah, we also do more testing for more scenarios. Actually, our prediction is more consistent compared to previous solutions. Yeah, for more challenging cases, for example, in the middle, which is the object is far away from the camera, and on the bottom, which is underwater scenario, we can still identify the animals, yeah, the movement of the animals and the depth, the geometry properties of them. So once we have depth information, so actually it has lots of applications. So for example, once we have depth information, we can combine with AIGC. So we have the input image, we can predict the depth information, then we can combine with, for example, control that. Then the regenerated images can maintain the same spatial structures and the geometry properties as the original input. We can also apply to video editing. So as you may be aware, for the video editing results, so this kind of geometry property is exactly the same as the original one. Yeah. So actually it can also be utilized into lots of downstream tasks, for example, for self-driving, for embodied intelligence, intelligent robots. Okay, so we open source our code base on, for example, on GitHub, and also our models, our demos on Hugging Face. So we have received lots of feedback from the community. For example, some of the researchers trying to transfer depth anything into, for example, TensorRT or ONNX, and some of them trying to combine it with, for example, transformer.js. and controllers or some mobile applications, for example, Android or iOS, and so on and so forth. So some of the cases we will show here. So apart from academia, we also received some feedback from industry. For example, Elon Musk from Tesla. So the major point is that they are vision-centric self-driving. Yeah, so which means no data, no data, no point cloud is needed. So if we have this kind of depth information, it can much benefit the self-driving with only vision-centric. Okay, so our model is also included in the Apple core machine learning models. So we have depth anything model. So actually for Apple Intelligence, if you want to design some fancy applications, you can just call the corresponding API. I actually, for example, this is a case, fancy case. So we have more cases, for example, more applications. Since we have depth information, so from single image, we can do 3D reconstruction from single image. So this is a researcher from Hugging Face. Yeah, so we can try to transform the head from 2D to 3D scenarios. And also for the things on the right, yeah, we can combine the anything with transformer.js. Yeah, so we can have more fancy applications. So we can convert the 2D videos into 3D videos. So for example, so previously when we're trying to do a phone calling or do video conference with our teammates or our families, we are using Zoom or we are using Facebook. Actually, there are 2D videos. But if we have this kind of depth information, actually we can have 3D videos. So actually we can have more fancy applications. So these fancy applications, so Wenbo also talk about using DepthCraft. Yeah, actually you can motivate more applications in or research in HCI, which is human-computer interactions. Yeah. So for example, so back to for about 20 years ago, what we are doing using our mobile phone. Actually, we have the keyboard. So actually you can think the interaction or the interface is 1D. We are using the keyboard. So back to 2007, so Steve Jobs released the iPhone. Okay, so what's the major difference? Is now we are switching from 1D keyboard to 2D screens. Okay, and after that, so nowadays it's 2025, about 18 years, but we are still on 2D screens. Even we have more fancy screens, for example, from Samsung or from Huawei. Okay, so or the newest version of Huawei phone, actually it has about 3 screens, but it's still on 2D. So compared to previous versions, they can try to, for example, include our laptop into mobile phones. But what if we have 3D? Actually, we can include our office into our mobile phones. So that would be quite fancy and lots of interesting applications. Yeah, so lots of things to investigate. Yeah, so is depth anything the end? So actually the answer is no. So last year there is also one important work, which is diffusion-based molecular depth estimation, which is Marigold. So we do some comparison and we find that depth anything we want is not so good as some scenarios. For example, for the fine details, for trying to figure out the depth of transparent objects, and also for reflections. Actually, the performance is not so good as Marigold. Yeah, so we are trying to figure out these issues. So how to figure out these issues? So actually, we do lots of experiments, and finally, we find where the issue comes from. Okay, so the issue mainly comes from the data. Yeah, since we are doing data scaling for 2.5D for depth estimation, so data is important, but what kind of data to use and how to use, when to use is also important. So when we dive into the data, we find there are lots of noise in real data, in ground truth neighbors. So even we call it ground truth, but we find still lots of noise neighbors. For example, when we are trying to get the depth information using a depth sensor, okay, we can find there are neighbor noise in transparent objects, okay? And if we are using still matching, trying to get the depth information, but we find there are label noise in repeated patterns when we are trying to do matching, okay? So if we are using structure from motion, we also find there are lots of label noises in dynamic objects when the humans they are moving, okay? So if we are using existing models, we can still find some label noise from the model predictions. So how to figure out this issue? So where our main idea for the second version is that we are trying to utilize some synthetic data. So what's the situation for synthetic data? What's the properties? So for example, when we check more details about synthetic data, what we can find, for example, on the top right part, we find that the depth of the synthetic data, we can get about 100% accuracy. For example, the structure of the plants and the building. And for virtual kitty, we can still find the accuracy of the depth very good. Okay. So we are trying to use this kind of data. So the question is not, okay, so can we use the synthetic data only? Yeah, regardless of the real data, only use the synthetic data only. Is that okay? Actually, the answer is no. So what's the problem? So the synthetic data has advantages, okay, it's 100% accuracy. But what's the disadvantages? What's the problem? Okay, what do we find? The first one is the distribution shift. Okay, so the synthetic data, actually, we are using some simulation platforms. So as you may be aware, so for example, the appearance, okay, the appearance, the textures, and the colors, actually, they are quite different from the real data distribution. So the distribution shift is a problem. Okay, and also for the second thing is that the thing is quite limited, the diversity is limited. Since we are using simulation platform, but available simulation platform is limited compared to diverse different scenarios in real things. Okay, so what we need to do? So we found that for purely synthetic data, we found they have highly processed, but we found some problems. There's some distribution shift between the synthetic and the real, and the diversity of the thing is quite limited. But we can use it to train our largest teaching model. And now we're using this teaching model to label some, to give labels to these unlabeled real images. And since we have massive number of unlabeled real images, so we can have lots of procedural labels. And finally, we can combine these labels from, for example, high quality labels from synthetic data and the procedural labels from vast amount of real data. So finally, what we have? So we have the high diverse and precise and learn fine-grained details of the depth information, geometry properties, structures, and also the distribution, real-world distribution. So this is our final student model. So we also do some interesting testing. For example, if we are using a synthetic data, and what if we naively combine all of them to do a joint training? But actually, if we do naive joint training, the performance is not so good. Yeah, so our final model actually compared to previous solutions. For example, when we do a comparison between Marigold and depth anything, we do actually our performance for the oil painting or for the foggy scenes or for the scenes with detailed structures, our performance is much better. Yeah, so this is our previous solution for depth anything V1. So the performance seems quite good. But if you do further comparison, so we want to push the limit for this task for molecular depth estimation. So actually for V2, we can further boost the performance, the structure more detail, and more geometry properties, and so on and so forth. Yeah, we also do some testing in video scenarios. So this is depth anything V1, and this is depth anything V2. Okay, as you may be aware, so the detailed structure is more accurate and also the consistency, but we are still doing frame by frame predictions. So recently there are some great works, for example, depth structure, video depth anything, and depth any videos, so on and so forth. Actually, they are doing video depth prediction. So we further do some testing. For example, this is on the abstract images and the paintings, and also for the right one, which is the self-driving scenarios. So these are the color case and the most challenging case. But we can find compared to the previous version. So V2, actually, we can get best performance. So actually, we have pixel level understanding. So this is the pixel level foundation models. So especially for the right part, if you find what you can find, actually, you can find there is a screen, there is a display embedded in the back of the chart. So actually, it clearly captured the current scene. Okay. So, but for depth anything V1, the predicted depth is in the wild. But actually for V2, it can clearly identify the real depth of the display, which is the same depth as the back of the chart. Okay, so this is important, and also for the abstract images. Okay. Yeah, so we also have some testing to our scenarios. Okay, so the first one, so yeah, this morning, sharing the screen. Oh, not sharing this one. Okay, can do. Yeah, so this one actually is a city center of the Nashville. Actually, we can have some predictions for the real things using depth anything with you. Okay, the next one is the music city center, the conference hall. Okay, we also do some testing outside the building and the depth predictions. So then we go to this conference room. So what we have? Yeah, we test the elevator. Okay, the crowded things and also the stairs. Yeah, just outside the room, just outside the room. I will also do some testing. So at the beginning, I listened to the great talk of Wenbo. Yeah. So this is the predictions. Actually, since Wenbo is far away from the back, so actually it's in these regions. Due to a display, actually we can identify. Yeah. So this is Wenbo. And if we take a closer capture of the speaker, we can still find the corresponding depth information. And then, yeah, we're also testing. So the great talk from Ethan. Okay. Now we also want to do some demonstrations. Okay. So what we can find. So yeah, maybe for yeah, actually for this program is running on my laptop locally. So but this laptop is bought about 5 years ago using Apple M1 chip. Okay. So I want to do some testing. Okay. But the speed is not so good. Yeah, so if trying to identify the relative depth of my left hand and right hand, okay, so you can find actually this one, yeah, my right hand actually is closer to the camera, but what if I switch the relative position of them? Yeah, we can find, okay, my right hand is far away from the camera compared to the left one, okay. So we can also do some testing to the audience. So let's switch to yeah, I'm not sure whether my computer can connect to my mobile phone. Oh, yeah, we can success. Okay, so first we do some testing. Thanks for the organizer. So we're trying to identify. Yeah, but there are some delay. Yeah, okay. Yeah, our speaker, yeah, our organizer, two organizers, the relative depth of the laptop and microphone, and also the chairs and desk. Okay, so how about our audience? Okay, I can do some testing. Yeah, okay, you can find, okay. So the chairs in the front and our audience in the, okay, in the back, and we can actually identify the relative depth. Yeah, so you can wave your hands, yeah, if you are interested. But there's some delay, yeah, since there are some, yeah, okay, the model is running locally. Yeah, okay. So actually we open source all of our code and also the demo on Hugging Face. So if you are interested, you can try to run the demo by yourself. Okay. So let's back to our slides. So I'm going to stop the demo. Yeah, so apart from the demo, we also have a video trying to demonstrate its effectiveness or performance in lots of diverse scenes. For example, the object is far from the camera, while in the crowded scenes in the hallway. And then, yeah, lots of things, the objects, the birds are far away from the camera. Detailed structures of the captured images, and also in foggy scenes, in transparent objects, and also abstract objects and self-driving scenarios, crowded scenes, AIGC generated images. Yeah, underwater and a crowded classroom and oil painting, transparent objects, foggy scenes. Yeah, color image and gray image. Okay, and final one, yeah, pay attention to the last one, the regions with broken window or unbroken windows. Yeah, so that's the difference. We can clearly identify the relative depths. Okay. Yeah, so in the first part, we just talk about spatial understanding, especially for 3D and 2.5D foundation models. Yeah, both of them belongs to pixel level foundation models in belongs to our workflow. So next thing I want to figure out is that we have the raw operators, backbone structures. The next thing we want to figure out is the representation learning algorithm. So this is quite important. For example, when we're trying to train CLIP, train Dino V2, we are using contractual learning or reconstructive learning. So what's about the thing for spatial scenarios? Okay. So what we did, so what we can find, so previously the most powerful feature extractor for images is a Dino V2. So it can well identify the relative positions or the regions from different images for the same object. So, but what's the situation in 3D? Okay. So what we can find for 2D, actually we have lots of, for ImageNet, it contains more than 10,000 number of images. It contains more than 10 million number of images, okay? And even actually we have web scale enabled images or weakly enabled images can be utilized for training our model. But for 3D scenarios, it's quite limited. For example, when we are trying to use ModelNet, only about 10,000 instances. Even now we have, for example, the observables, but the size is quite limited, less than 1 million, okay? So what we are doing, the first thing we are trying to do is to unsupervised representation learning, unsupervised 3D representation learning. So we have our mask scene contrast. So actually we have two objectives, which is contractual objective and the reconstruction objective. Yeah. And then another problem is that, so we may capture point cloud from different scenarios. So at the beginning we talk about we come from the Vision Pro, we come from self-driving cars, we come from our mobile phones, or 3D model assets, yeah, or scanner and so on and so forth. So, but for different point cloud, they have different properties. For example, for indoor scenes, usually the space is small, but the point clouds, they are dense compared to for outdoor scenarios, where the space is large, while the density is small. So how to do multi-data joint training is also important. So actually, we also have a solution. So this is published in last year's CVPR 2024. So we have point prompt training. So for the data set from different sources together, different domains together, and finally train our prompt adapt. So this is CVPR 2023 and 2024 work. So what we have done for 2025, this year CVPR. So we have our Sonata. So we first find some problems with previous solutions. So given the input, we have some existing solutions, CSC or MSC, while we find there are some geometric shortcuts for these models. For example, finally, they may converge to the height and also the surface normal of the existing thing, but this is not what we want. So we want to figure out this issue, the geometry shortcut. So what do we have? We have our spatial representation to the limit, which is Sonata. So we have different properties. Yeah, we get a better performance when we are using self-distillation methods. And we have a linear property, yeah, which is based on our previous backbone structure, PTV3. Okay, and we show some interesting application. For example, we can be semantic awareness. Yeah, we are trying to identify the corresponding between different objects, between different parts, different semantics. We can have spatial reasoning. Yeah, we can do reasoning across the 3D scenes. For example, here is a comparison. So we have our input. So we have Dino V2. So Dino V2 can extract good semantics, but for geometry properties, it's not so good. But for our Sonata, it can better illustrate the geometry properties for spatial representations. Yeah, so we can do further comparison. For example, for Dino V2, we have good semantics, but the geometry property is not so good. And for Sonata, the performance on the geometry is good, but for semantics, for some regions without much geometry property, the performance is not so good. And if we are trying to combine all of them, actually, finally, we can get the best compilation of them. Yeah, so actually, a new work is submitted to NICS NUPS, which is Consental, which is trying to combine using a most powerful 2D representation learning model and 3D representation model, Dino V2 and Sonata. First, get our Consental to NICS. Yeah, and we can do some interesting testing. For example, we can have zero-shot representation cross scenes. We can do retrieval. For example, you can count your text description or query description, and then you can identify the corresponding parts or objects or regions contained in the 3D scenes. Yeah, so apart from the basic foundation models with understanding with representation learning algorithms. So the next we want to identify is reasoning, spatial reasoning. Okay, so what we have. Actually, so previously we talked about actually we can combine or introduce large language models into visual modalities, into images and into videos. We can also combine them with 3D things. So we have multimodal 3D foundation model, GPT-4 points, so which is also published in last year's CVPR. So actually we can do lots of tasks. For example, we can do 3D recognition, 3D captioning, 3D QA, and generation. Yeah, but for this work, it's only focused on the objects. But for our real things, we want to switch to thing. So this year we have our new multimodal 3D foundation model, which is GPT-4 thing. So apart from point clouds, we can also be 3D awareness from the videos. Yeah. So actually for this one year, that's we are trying to understand the 3D things from the videos with visual language models. And for lots of applications, so once we are trying to manipulate or grasping the objects, the directions or the orientations of the objects is also important. So for this year's ICML, we also have the object orientation estimation, which is always anything. So we test in different scenarios, indoor scenes, outdoor scenes, paintings, and so forth. Yeah, for the animals and for the images in the wild, and also for some video demonstrations. Okay. So let's pick an airplane and a car. Okay, we are trying to estimate all the orientations of the object. So we can do some testing. So the previous solutions, for example, the previous agent, GPT-4 and also the Gemini 1.5 Pro. Actually, if you are given for example, given an image, you ask a question, actually, they are not performing so well trying to understand or trying to do reasoning for the spatial relationships. Actually, if we are combined or anything, the performance would be much better. So we also have some works on CVPR 2025. Yeah, so previously we have clip, okay, but it's not spatial awareness. So we have spatial clip and corresponding if we, for example, previously we have Llama, we have mini GPT-4, but it's used the clip. But if we have spatial clip, we can also have spatial Llama. And also at the same time, we have proposed a corresponding benchmark to boost the performance and to validate the performance. Yeah, and also egocentric vision is also important, especially for embodied agents for robotics. So for this work, we are trying to empower large language models with 3D situation awareness. So for example, for the given robots in a camera scene, for the egocentric capture the images or videos, we are trying to understand the 3D relationship or 3D situation awareness. Yeah, so this is also in this year's CVPR. Yeah, we also do something interesting or unified model for example, here is for 3D scene understanding and generation at the same time. So which is unified driving world models. Okay, so then at the same time, we can do understanding, we can do generation forecasting. So which is can much benefits the next, for example, planning, action, and so on and so forth. Is for self-driving scenarios. Yeah, we also have some other works, for example. So previously we are trying to do simulation to real, but actually we can also do real to virtual simulation platform. So we can have interactive and immersive interactions with real things. So what we did,
while 3D reconstruction methods like
so after the videos, we can do 3D reconstruction.
Realism.
Yeah, for example, using the for 3D but previously the reconstructed things. Okay, we see the quality is good, but then how to use this kind of reconstructed things? So actually, we have different applications. For example,
PBR materials.
we do reconstructions. Now we can have some. Yeah, we can have physics-based interactions. Yeah, so this is the real thing captured in the living room. Now we can have interactions, physical interactions. Okay. Yeah, so this is a conference room. We do reconstruction. So once we have this kind of reconstruction, we can do interaction. So at the same time, we can also have a robot in the scene. Okay. Then we can also do some modifications. So we can modify the texture, the color, and also some of other properties according to the appearance. So once we have these informations, so we can match benefit or argument our existing data for embodied intelligence. Yeah, so the next I want to talk about is that, so previously we have depth anything V1 and depth anything V2. And then, but all of them are relative depths, but the most important application. But for some of the applications, for example, AIGC, so relative depth is enough. But for some important applications, for example, in self-driving, in embodied AI, so metric depth is important. So we want to extend depth anything V2, the relative depth into metric depth. So actually we have prior depth anything, anything. Yeah, so currently is available on arXiv. So what's the property and what's the core design? Okay. So what we can find existing depth anything model. Okay. The good thing is that the fine details, complex content, and good geometry. But the bad thing is that unscaled metric. So, but we have some properties from existing data. For example, we can have some processing metric. For example, we can from structural motion from sensors. So even though we only have very sparse kind of distributions or point cloud or this kind of depth information, but finally we can get combine the advantages of these two domains. For example, even though in the middle for the current metric measurement, so ignore details, incomplete content, missing geometry. But the good thing is that we have present metric. So if we do a compilation, we have prior depth anything. Yeah, so which can output the detailed metric depth information from a single image. So this is important. Yeah, but we treat this as a maybe depth anything V2.5. No, this is not depth anything V3, but we also have something keep in mind. We are trying to have depth anything V3, which is the real metric depth anything even without this kind of prior information. So this is ongoing work. Okay. Yeah, so due to time limits, I will not go to more details about this part. So the final thing I want to figure out is that, yeah, so we have a demo here. Right, so this is a movie from, yeah, more than about 100 years ago from Charles Chaplin, which is the lion cage. So the actor, yeah, so goes into the lion cage. So he wants to escape from lion cage. Okay, so tries to open the door, but unfortunately he closed the door. Okay. So he wants to seek help from the pedestrians, but seems nobody is around. So he tried to figure out another solution, another way out. Okay, seems there is a door nearby. Okay. Okay, so he escaped, but the best thing is that there is a tiger in another cage. Okay, so the thing I want to investigate, so the visual intelligence. So nowadays, actually, we have lots of multimodal natural language models. The problem or the generalization ability, reasoning ability is quite good. So it's natural language model powered. But for visual intelligence, for example, when we're watching a video, when we're watching a movie, actually, there are no language interactions between our and the actors, but we can still understand the sense of the humors of the actors. So actually, what about pure vision-based visual intelligence? So this is an open problem since compared to 1D or 2D, or existing, especially compared to 1D, we have unified structures, we have unified tasks for different language or text corresponding related tasks. But for vision, it's hard for us to identify, for us to unify and to scale up. But I think we still have an ability to find a solution for pure vision-based visual intelligence. So this is what our humans will have. Okay, so I think this is the end of today's talk. Thank you.
Thank you for the great talk and amazing demos. So we are out of time, but because it's lunch break, I think you can take some questions if you're free.
Yeah.
And our afternoon session will start at 1:50. So please feel free to have lunch or ask questions.
I mean, I do have a question.
Oh, okay. Yeah.
So, like, there's some.
Yeah.
Okay.
Oh, yeah.
I really like to talk. How long did it take to create the reconstructions that you showed? Like the reconstructions that were used before, like the physics-based?
Yeah, so actually we are using existing solutions. Yeah, for example, we are using the state-of-3D GS-based reconstruction methods. Yeah, so the good thing is that we can match argument the data available for downstream tasks, for example, for manipulation grasping in embodied intelligence, compared to existing simulation platforms. Since existing simulation platform, the diversity of the scene is quite limited, but actually if we can transfer all the real scenes into simulation platform or into reconstructed scenes, so that would be much better.
I see like another high level question, which is that, so yesterday, like in, Kiana and Shani's talk, and she was talking about how interaction can be a way to better understand the scene. And I think it's interesting because you've done like such amazing work on understanding a scene to therefore enable like interaction. And so I'm curious like what you're thinking about like that paradigm is.
Yeah, I think one important thing actually is also what we are trying to figure out is physical AI, which is physical understanding, generation, and also manipulation. Yeah, so currently we know some properties. For example, we have semantics, we have some geometry properties, but for the interactions of the real world, for example, the materials of these objects is also important and some other properties. So, but for our real robots, we want to have some interactions. So the lots of physical property is also important. So I think, for example, if we can use some physical AI or physical understanding and even generation, we have some powerful AIGC models. But these models, the demonstration is quite good. The quality, the appearance is quite good. But I don't think the physical property, the physical law is contained in these videos. So I think this might be a future direction that we need to figure out. Okay, thank you.
Hi, thank you for the talk and the work. Amazing. I had a quick question, just from a high level. As we think about depth estimation, the work in DVT and then depth anything 1 and 2, a lot of that leverages like large data sets, right?
Yeah.
Student teacher model. The move from real world to synthetic data now showing a lot of improvement. Do you think there's any benefits or gains to be had in modifying the models themselves? Because we're seeing a lot of improvement in the data.
Yeah.
But what about now in the model itself? Changing the DVT maybe or something like that?
Yeah, I think that is a good question. Yeah. So actually, most of our methods are data scaling, and now we can say the performance, especially the generalization ability, is quite good. But if we look into the details, okay, if we look into the details, for example, this is a past surface. But if we look at the depth, actually there are some points up the surface and down below the surface. But actually, if we have some constraints, for example, if we introduce some mathematical constraint prior information or some geometry prior information or physical prior information into our network design, and I think this kind of problem can be solved. And also at the same time, maybe we don't need that much amount of data. So actually, I think this is also an opportunity for our researchers or students in university. We can figure out compared to research in industry. I think that might be, but I think that is also a challenge. Since how to design this, how to formulate is also important. Okay, thanks for a great question.
Sorry for interrupt, but it was the last question for the official workshop schedule for the morning session, but feel free to reach out to the speaker if you during the lunch break. Thank you.
Okay, thank you.